Today, Internet communications are secured with public key cryptography. In 1994, Peter Shor found a quantum algorithm that will break virtually all public key cryptography that we know today. Shor's algorithm has polynomial complexity, whereas classical methods for breaking public key cryptography have exponential complexity. Exponential complexity for classical methods for breaking public key cryptography means that if you increase the length of your secret key by just 1 bit, that will cause the efforts required to break this cryptography to double. Whereas in Shor's algorithm, so if one increases the length of a public key by 1 bit, then the efforts required for breaking this public key cryptography will just increase incrementally. Even if you double the length of a public key, then with Shor's algorithm, so you will have to invest just 4 times the amount of efforts compared to the current length of the key. This essentially means that current public key cryptography cannot be used if one has access to a quantum computer that is capable of running Shor's algorithm. Our next big goal in this course is to understand and analyze Shor's algorithm. In order to do this, we have to start with the mathematics underlying public key cryptography. So this is mathematics of remainders and applications of group theory to remainders. So we fix an integer m greater or equal to 2 and consider the set of remainders modulo m. So that is remainders after division by m. So possible remainders after division by m are 0, 1, 2, 3, all the way up to m minus 1. So m minus 1 is the largest remainder because m has a remainder of 0. And so this set is denoted as Zm. So there are 2 basic arithmetic operations on the set M. So there is addition and multiplication of remainders. So if we consider Z9, then in this set of remainders, 7 plus 8 is equal to, well, 15, but this is 6 mod 9, and 7 times 8, so that's 56. But so 54 is divisible by 9. So if we subtract 54, we get 2 mod 9. So this is how addition and multiplication of remainders work. And so we say that the set of remainders forms a ring. So here, a ring is an algebraic structure with 2 basic operations of addition and multiplication that satisfy natural properties that we expect. So I'm not going to mention the definition of the ring. Most of you know it. We will be particularly interested in the operation of inversion of remainders. So that is looking for multiplicative inverses. So for example, in Z9, 7 times 4, so this is equal to 28, and 27 is divisible by 9, so this is 1 mod 9. So if the product of 2 remainders is equal to 1, then these 2 remainders are inverses of each other. So this means that 7 inverse is equal to 4, and 4 inverse is equal to 7 in Z9. Now, in Z9, some remainders are invertible, but others are not. So, for example, 3 does not have an inverse. In Z9, because so 3 times x equals 1 mod 9 has no solutions. Well, simply because 3 times x is always divisible by 3, even if we add multiples of 9, so this cannot be equal to 1. So we have a very elementary theorem that tells us which remainders are in fact invertible in Zm. So we have a theorem so that says that remainder k has an inverse in Zm if and only if the greatest common divisor of m and k is equal to 1. So, for example, here the greatest common divisor of 9 and 7 is 1, and so 7 is invertible. But the greatest common divisor of 9 and 3 is not equal to 1, and 3 is not invertible in Z9. So let us go over an example that illustrates how we find inverses of remainders. So here we have a problem. Find the inverse of 901 in Z 2020. Now, first of all, so this theorem tells us that this inverse exists because the prime factors of 2020 are 2, 5, and 101. And 901 is not divisible by any of these prime numbers. So this means that the greatest common divisor is of 2020 and 901 is equal to 1. So by this theorem, this remainder is invertible. So now, since we know that the greatest common divisor of these two integers is equal to 1, what we can do is we can apply Euclidean algorithm to verify this fact. So here we run Euclidean algorithm for finding the greatest common divisor. So what we do is we take the larger integer, 220, and divide it by 901 with the remainder. So this is 2 times 901. So this is 1802. So the remainder is 218. So then we take 901 and divide it by 218 with the remainder. So we say 901 is equal to 4 times 218. So what do we get? So here we get 840 and 32, 872, so plus 29. So then we have 218, and we divide it by 29. So 29 is almost 30, so here this will be 7. So 7 times 29. So this is what? 7 times 30 is 210, minus 7 is 203. So this means that this is 203. And so the remainder is 15. So then 29 is 15, or 1 times 15 plus 14. And finally, 15 is equal to 14 plus 1. And this 1 is the GCD that we are seeking. So the second stage of the extended Euclidean algorithm is now we run this calculation backwards. So that is, we start with a 1, and we write 1 as the difference of 15 minus 14. Well, this is certainly true. So then we go to the next equality, and we express 14 in terms of 29 and 15. So we have 15 minus, well, 14 is 29 minus 15. And so we get 2 times 15 minus 29. That's certainly true. This is 30 minus 29. That is equal to 1. Then we go to the next line, and we eliminate 15 as 218 minus 7 times 29. So we get 2 times, well, instead of 15, we write 218 minus 7 times 29 and minus 29. So now we simplify. So that is 2 times 218. So here we have minus 14 times 29 and minus another 29. So 14 plus 1, that's 15 times 29. So now we go to this line and we eliminate 29. So we get 2 times 218 minus 15 times. So instead of 29, we write 901 minus 4 times 218. And now we collect terms. So with 218, so we have 15 times 4, that's 60, and it becomes with a plus 2. So we get 62 times 218 minus 15 times 901. And finally, we go to the last line, and we eliminate 218. So we get 62 times 2020 minus 2 times 901 minus 15 times 901. So that equals 62 times 2020. Then here we have 124 and 15. So we get minus 139 times 901. So if we use a calculator, then we can verify that this is indeed equal to 1. So here we have 125, 240 minus 125, 239. And the difference is indeed equal to 1. Now we take our last equality here. Right, so we have 62 times 2020 minus 139 times 901 is equal to 1. So this is an equality with integers. And now we take the remainder of both sides after division by 2020. And so this 2020 will become 0. And so what we get is minus 139 times 901 is equal to 1 mod 2020. And so this tells us that the inverse, multiplicative inverse of 901 is equal to negative 139 in Z 2020. But what is negative 139? So that's the same as 2020 minus 139. And this is equal to 1881. So our conclusion is the inverse of 901 in Z 2020 is 1881. Now let us build the bridges between remainders and group theory. Well, first of all, so we say that Zm forms a group with respect to addition. And this was the first group that was historically used for cryptography with Caesar's code. So, however, for modern cryptography, this group is too weak. So the crypto systems based on this group are very weak. And a better group is we take Zm star. So this is the set of invertible remainders forms a group with respect to multiplication. So for example, Z9 star is the following set. Well, 0 is not here because 0 is not invertible. So, and then we know that we should exclude remainders that are not co-prime with 9. So that is divisible by 3. So we get 1, 2, skip 3, 4, 5, skip 6, 7, 8. Right. So here we have a group with 6 elements, and so the operation here is multiplication. An important special case is when the modulus is a prime number. So let P be a prime number. So then ZP multiplicative is, so because every non-zero remainder is co-prime to P. So this means that this group contains all non-zero remainders. An important parameter of a group is its order. So order of a group G is the number of elements in this group. So this is denoted by G in vertical bars. So what we have here is that the order of ZP multiplicative, if P is a prime number, is P minus 1. Because we have P remainders in total, and when P is a prime, we only have to exclude 0 and to get a multiplicative group. So the order of Z9 multiplicative is equal to 6. And in general, so what's the order of Z P to the n multiplicative? So here we need to exclude remainders that are divisible by P. And so it's clear that, well, the total number of remainders is P to the n, and the number of remainders that are divisible by P is P to the n minus 1. And so the order of this group is given by this formula. How can we find the order of the multiplicative group Zm if m is not a power of a prime? So the answer here is given by the Chinese remainder theorem. Let k be a divisor of m. So then we have a natural map from Zm to Zk, where we take just remainder mod k. So this is a ring homomorphism. So this means this operation preserves addition and multiplication. Right? So for example, so if we have Z9, we can further reduce it to Z3. Right? So like we cannot reduce it to Z4, so this will not be a well-defined map, but reducing mod 3 will be a well-defined map, because adding multiple of 9 does not change a remainder after division by 3. So we have the following theorem. Suppose M is equal to K times S, where these two factors are co-prime. So GCD of K and S is equal to 1. So then, we have the following map. So we can take Zm and we can reduce things mod K, or we can reduce things mod S. And so now we can do double reduction. So this means to each remainder mod M, we associate a pair of remainders, one remainder mod K and another remainder mod S. And the claim that this is an isomorphism of rings. So in particular, if we have a pair of remainders, one remainder mod K and another remainder mod S, then we can find a unique remainder mod M that will produce this pair. As a corollary, we get the following, that the multiplicative group of Zm, so the set of invertible remainders, is isomorphic to the product of the group of multiplicative remainders mod K with a group of multiplicative remainders mod S. So let's do an example. So let's consider Z15 multiplicative. It consists of remainders that are co-prime to 15, that is not divisible by 3 or 5. So we have 1, 2, 4, we skip 5 and 6, 7, 8, skip 9 and 10, 11, skip 12, 13, and 14. And so we claim that this multiplicative group is isomorphic to Z5 multiplicative cross Z3 multiplicative, where so Z5 multiplicative is the set 1, 2, 3, 4, and Z3 multiplicative, well, 3 and 5 are both prime numbers, so we just exclude zero remainder. And now let us look at this map. So here, 1 from here is mapped to, so we reduce 1 mod 5 and mod 3. So in both cases we get 1, 1. So 2 is sent to a pair 2, 2. So we reduce mod 3 and mod 5. 4 is sent to a pair, well, reduction mod 5 is still 4, but reduction mod 3 is 1. Then 7, reduction mod 5 gives us 2, and reduction mod 3 gives us 1. Then 8, reduction mod 5 is 3, reduction mod 3 is 2. Then 11 is reduction mod 5 is 1, reduction mod 3 is 2. And then 13, reduction mod 5 is 3, and reduction mod 3 is 1. And finally 14 has reduction mod 5 is 4, and reduction mod 3 is 2. And so what we see is we obtain here all combinations of pairs where the first element is in Z5 multiplicative, and the second element is in Z3 multiplicative, right? So here we have 8 elements, and which is 4 times 2. For RSA crypto system, we will be interested in the following case, when M is the product of two large prime numbers. So P and Q are prime. Then in this case, we can write down the formula for the order of the multiplicative group Zm. So this is the order of Zp multiplicative times the order of Zq multiplicative, and by Chinese remainder theorem. And because both P and Q are prime numbers, So the first order is equal to p minus 1. And the second is q minus 1. And so this tells us the number of elements in the group Zm multiplicative when m is the product of two primes. The reason why the order of the group is such an important parameter is the following Lagrange's theorem. So let G be a group of order n. So a group of order n. So this means that there are n elements in this group. Then for all elements A in the group, A raised to the power n gives us identity. Let us apply this Lagrange's theorem to ZP multiplicative, where P is a prime. So we get the following corollary, which is called Fermat's little theorem. Let P be a prime. Then for all A in ZP multiplicative, A to the P minus 1 is equal to 1 mod P. So here, the fact that A belongs to ZP multiplicative, this means that A is not divisible by P. And that P minus 1 is the order of the group ZP multiplicative. Here we only have to delete the zero remainder. And so the consequence of Lagrange's theorem is that A to the P minus 1 is always equal to 1 mod P. So for RSA setting, we have M is the product of two primes, P times Q, where P and Q are primes. So in this case, as we have calculated, the order of the group, so n, which is the order of Zm multiplicative, is equal to the product of P minus 1 times Q minus 1. So then Lagrange's theorem will be stated in the following way. So if A is not divisible by P or Q, so this means that A is an element of Zm multiplicative, then A to the power P minus 1 times Q minus 1 is equal to 1 mod PQ. So this is the statement of Lagrange's theorem for the setting of RSA. This property will be used in the construction of RSA cryptosystem that we'll discuss in the next lecture.